Hello everyone, I am Deepak Jadhav from University of Erlangen-Nuremberg in Germany, and today I'll be presenting my research on phase field modeling of dynamic fracture using a modified asynchronous variational integrator. First, I will introduce the topic. So, phase field models approximate the discrete crack with a smeared crack of length of width epsilon. When this epsilon tends to 0, the phase field energy functional actually converges to the discrete energy functional. So to get accurate simulation results, we need epsilon very small. And to resolve very small epsilon, the very small length scale parameter, we need very small mesh sizes. Particularly in dynamic simulation, what happens is when you use small mesh sizes, the smallest mesh element dictates the global time step. So it's really computationally expensive. So to avoid this problem, what we do is we use asynchronous variational integrator that employs different time steps for different elements. So it uses a little bit bigger time step for the cursor elements, which results in lower updates, and that leads to the computational savings. So we'll have a look at the AVI for linear electrodynamics. So AVI basically stands for asynchronous variational integrators for linear electrodynamics. So we define Lagrangian as the difference between kinetic and potential energy. Then we define action as space-time integral of the Lagrangian. And then we use Hamilton's principle of least action, which says that physical trajectory of the system renders the action some stationary. So what we do is we take the variation of the action equated to 0 to get Euler-Lagrange equations. And these equations can be solved using finite element method in space and Newmark's method in time in the continuous setting. Let's have a look at the discrete setting now. So in the discrete setting, we define the discrete Lagrangian and space-time integral of the Lagrangian on one element. We define the discrete action sum as the sum of the discrete Lagrangian on all the elements and on all the time step. Then we use discrete version of Hamilton's principle to get discrete Euler-Lagrange equations, which we can derive like this. We take the variation of the discrete action equated to 0 to get the discrete Euler-Lagrange equations. Now, the discrete Euler-Lagrange equation can be solved in two ways. Either it can be solved synchronously or asynchronously. As you can see, in this 1D mesh, there are three elements, and all these three elements have the same, let's say, time step size. And here you see the smallest element has a small time step, and the cursor element has the relatively bigger time step. So what happens is cursor elements get updated less frequently. So this will get updated 2 times, and this will get updated 3 times. So this leads to computational savings. So we formulate the discrete action for linear electrodynamics, take the variation of the discrete action equated to 0 to get the discrete Euler-Lagrange equations. Then what we do is we use a notion of priority Q to solve the equation shown here by using asynchronous, to solve this equation asynchronously. So priority Q holds all the element in a queue with appending order of their activation times. So the smallest element will have the least activation time, and the largest element will have the higher activation time. So element with the lower activation times get the first priority. So what we do, we pop the element, update the displacement based on the momentum of the previous time step. Then we update the momentum for the next time step based on the current configuration of the displacements. And when the simulation time of the element is greater than when the activation time of the element is greater than the total simulation time, we kick that element out of the priority queue. And we repeat this procedure until the priority queue is empty. So here you can see it's 1D mesh with 3 elements. We compute the time step of an element using the CFL condition. And here you see these elements get updated first. Then this will get updated first. This will get updated in the 3rd place. And after that, this will get updated in the 4th place. And so on until the priority queue is empty. Now we wanted to apply the same concept to study the dynamic phase field fracture. So we define the action for the dynamic phase field fracture as follows. This shows the kinetic energy term minus, this is the potential energy term. Here you see this is the elastic potential energy, C is the phase field energy, and this is the material degradation function. And here you see the crack energy. We take the variation of the action equated to 0 to get two coupled Euler-Lagrange equations. These coupled Euler-Lagrange equations can be solved using finite element method in space and Newmark method in time in the continuous setting. Similarly, we form the discrete action for the dynamic phase field fracture and take the variation of discrete action equated to 0 to get the two coupled discrete Euler-Lagrange equations. Now what we can do is we can solve this equation just like before. We use the momentum of the previous time step to compute the displacement of this time step. Then we solve this elliptical partial differential equation on element to compute the phase fields, and then we update the momentum by using the calculated displacements and the phase fields. But solving via above proposed method results in diffuse cracks. It does not give you sharp and well-defined cracks. To solve this problem, NEO proposed the method of using elemental patch. We call this method PSAVI, patch solved asynchronous variational integrator. So let's see what a patch is. The patch is a collection of all the elements which shares the node with the current active element. So we form minimization problem on this elemental patch by taking the hollow nodes as the constant values and by taking the filled nodes as unknown values. And then we solve the minimization problem on this patch to get the phase field value of the current active element. So what happens is it solves the problem for the dispersed crack patterns or diffuse crack patterns. But what happens is there is a fundamental problem in this approach, which I would like to present. Here it says like the surrounding affects the phase field value here. But what happens in elliptical partial differential equation is that when there is any perturbation in the domain, that perturbation should travel at infinite speed throughout all the domain. So this characteristic was not captured. So as the surrounding just affect the values of the active nodes, and when you change the active nodes, the effect should be felt by the entire domain instantaneously. That was not captured. So, and also it has a relatively high computational cost because you have to store the address of the surrounding nodes and has relatively obviously the complex implementation. So to solve this problem, what we do is first we solve for the phase fields, keeping the mechanical fields constant. Sorry, we solve for the mechanical updates by keeping the phase field constant. Then what we do, when the largest elements get updated, we freeze the displacement field at un star. We compute the history variable by using Mie's history variable approach. And finally, we solve the phase field globally after the largest elements update. So what happens here that we are solving the equation globally. So it really manages the propagation issue. So by using this approach, we also didn't get any diffuse crack patterns. So we also get the sharp crack patterns. And we also solved the fundamental problem of infinite speed propagation in elliptical partial differential equations. And it has relatively simple implementation and low computational cost, as you will see in the next slide. Here you see this is the 1D mesh with the 3 elements. We update the phase field when the largest elements get updated. So here we just have 1, 2, 3, and 4 updates. But here, if you see, here you update the phase field after every displacement update. So here you have, let's say, 6 updates for the phase field. So let's have a look at numerical example. We have a pre-notch linear elastic rectangular plate under tension. Tension applied is 1 megapascal on both the sides. Sorry. We have kept the mesh size h by 2 in the anticipated region of the crack propagation and h everywhere else. And then we study the distribution of the phase field. Distribution of phase field obtained is consistent with the already published literature. Also, we studied the crack tip velocity in 80 microseconds. So you see that the values calculated by our approach that I call GSAVI is globally solved asynchronous variational integrator, and this is patch solved asynchronous variational integrator by Neo et al. So if you see, the results are quite consistent. The results for potential energy are also quite consistent, but we report slightly higher values. Results for kinetic energy are also quite consistent, but at the end, GSAVI, that's globally solved asynchronous variational integrator, our approach reports a little bit higher values. And when you look at the crack energy, we report a little bit lower values because it's obvious that more energy is trapped in the form of kinetic and potential energy in the sample. We have also devised a convergence framework to study the convergence of GSAVI. So we derive a variational convergence framework. We study the convergence of discrete action and fit this into the power law shown here. So what we do is, after fitting this, we observe the convergence of 0.59. So we can say that method has a sublinear convergence, and it converges sublinearly when the spatial refinement is done. And about the crack, as you can see here, can we click on the crack, please? So crack propagates initially horizontally, and then it's distinctly bifurcates into two branches, and then it reaches the right edge. Simulation results are quite consistent with the experiments as well. So let's have a computational cost comparison here. It's the GSAVI, our approach. PSAVI is the approach by the new, and this is variation integrator. You can see that GSAVI needs almost half the computational cost as compared to VI. And with PSAVI, while both methods has the same number of mechanical updates, the GSAVI has less phase field updates, resulting in computational savings. So finally, I would like to summarize that our new implementation, globally solved asynchronous variational integrator, has relatively straightforward implementation. It also produces well sharp defined cracks. It also solves the fundamental problem that accounts for infinite speed propagation in elliptical partial differential equations. Also, it captures the complex dynamic fracture behavior and also delivers the significant computational savings. And we also studied the convergence of method, as can be seen here, as I showed already. It also shows the sublinear convergence with the with spatial refinement. And in the future, we would like to incorporate our new GSAVI with already developed spatial adaptivity method to develop new spatiotemporal adaptivity methods for phase field fracture. We have published these two researches on spatial adaptivity in the phase field fracture. With this, I would like to thank German Research Foundation and Frascal for making this research possible. And I thank you all for your attention. Thank you.